All right. Hi, everyone. So it's 6 o'clock now. So I'm going to go ahead and get started with our discussion for today. Yeah. So just give me a minute. I'll share my screen. And I'll begin the presentation. So let's start from the beginning. Whoops. Yeah, I got to share this. Okay. Here we go. All right, let's from the beginning. So today's discussion will be about trees and traversals. So the first thing we're going to do is we're going to go over the pre-response question, like the quiz 3 on this topic. And then we're just going to talk about like cheating and collaboration policy. And then binary trees and traversals, and then binary search tree question. Okay, so yeah, let's start with the review of quiz 3. I know it's a little difficult and it probably took a lot of people a long time, which I get, it's hard quiz. So I know it took me a while too when I first saw it. But yeah, let's remember what it was. You're given sorted data in the form of a linked list. Given a single linked list of integers that represents data set. With head node as the head, in this case 2, return the inner quartile range of the data set. So that's Q3 minus Q1, right? So basically it's right, it's the median of the right half minus the median of the left half. But it as you guys may remember, it's not as simple as that because there are like different rules about length of it. So let's go ahead and look at the code of like a possible solution and walk through it, and then we'll see an example and like how we came up with it. Right? So one thing that might be nice to have is like just looking at the code at the beginning, right? We have a Q1, a Q2, a Q3, and like the ends of the list as well. And this might be nice to have because it allows us to kind of like visualize it, but also know all the important data, right? Because you know, it might be useful to know the median, might be useful to know Q1, Q3, and then also the ends of the list, right? But also the other thing we can think about is kind of feels a little bit like finding the median of a list because, okay, yeah, that's part of it, right? But maybe it feels like it's the kind of question where you use a slow pointer and a fast pointer. So that's exactly what we use here, right? And especially because you can only traverse it once. So fast pointer, slow pointer is way to go. And this isn't the only solution. You may have come up with other ones, but this is, I think, a pretty reasonable one. Yeah. So also remember that there are 4 cases, right? Because like you need like the 4 different values, right? And so ultimately you can kind of split it up into 4 cases. Like on the list is just by 4, or like just by 4, or if like if you divide by 4, it's a range of 0, 1, 2, or 3, right? And the reason why we have these 4 different cases is because it's like the Q1 and Q3 are median of medians. So halfway you have like 1/2, and then halfway between 1/2 and the beginning is like 1/4. So you need to know what happens at like the 1/4. So that's why we need to consider those 4 cases. Yeah, so those are our 4 cases. And of course, like for slow pointer, fast pointer, we have 3 slow pointer. Yeah, one slow pointer, which like goes through really slowly, and 3 fast pointers. But the fast pointers go at different speeds, right? Because one needs to go, like we want the slowest pointer to only go 1/4 of the list, and then the fast pointers to go 1/2 the list, 3/4 the list, and the full list, right? So if we think about that as well, like one of them goes only 1 space forward each time, one goes 2 spaces forward each time, one goes 3, and the other one goes 4, right? Or yeah. So that's kind of what we have here, right? We go, this one goes 1 space, this one goes 2, 3, this one goes 4, right? So then once we do that, right, we have at the end, we want to be able to calculate the IQR. So then of course we have 4 cases, right, depending on how the list is. And if you remember, based on the link that was provided with the separate question, if the length of the list, the whole list is even, we're going to include the median, the values we use for the median in our calculation for the IQR. And if the length of the list is odd, we don't. So it might be easier just to see an example. So let's do that. So looking at this example, right, if we have 4 different cases here. Right? One with we have the length of the list mod 4 is 3. length list mod 4 is 0, length list mod 4 is 1, and length list mod 4 is 2, right? So the first one we're going to look at is with length list mod 4 is 3. And again, this is one of the 4 cases we consider these 4 good. So in this case, right, it's pretty straightforward because, again, it's an odd length, so we don't have to include the median. And in this case, because it mod 4 we get 3, we're also guaranteed that like each of the 2 halves of the list are also going to be of odd length, right? So because of that, we don't really need to do anything else. We just take Q1 here and Q3 here, and just Q3 minus Q1. We don't have to do any extra work because there's only one median for each of the halves of the list, right? This half list is exactly in the half, or exactly halfway, and then we get this one and this one. And like, there's nothing else we need to do. So we can just return Q3 minus Q1. For the second case, where mod 4 we get 0 for the length, we have that 1, 2, 3, and 4, right? And in this one, it's a little more difficult because halfway through, right, the median is going to be the sum of these two divided by 2, but that's what the median is. We don't need to find the median, we need to find the IQR. And again, for length even, we do include the median in our calculation of IQR, right? So what we do here, if the length is even, right, is we're going to take the sum of these two, right? Because we want the Q2, right? Or we want, sorry, Q1 and the one that comes right after Q1, right? Which in this case is Q2. So yeah. Well, it happens to be Q2 because it's only length 4. We just take the Q1 and the thing right after Q1 and average them to find our median, right? Because of the way we went through our list, we happen to always get the lower of the halves. And the same thing with Q3, right? Like we have to include the median, which was 3 as part of the calculation of the median. So we do 3, we average 3 and 4 for Q3, right? Because it's each half, you can consider like 2 halves, right? Is of even length. So we have to find the median of 2 even length lists. So we find the midpoint. We already know the lower midpoint is Q3 in this one. We already know the lower midpoint in this half is Q1. So we just take Q1 and Q1 and the thing right after Q1 and average them. In this case, we take Q3 and the thing right after Q3 and average them. And then we do the larger one minus the smaller one. And we get our IQR is 2, right? So 3.5 because 3 plus 4 divided by 2 and 2 plus 1 divided by 2. We get 2, right? After subtract. Okay, our next case is with mod 4 for the length we get 1. So for example, right, we have length 5, right? So 5 mod 4 is 1. And again, odd length. So we don't include the median in our calculation. So we just basically split around the median. So it's going to end up looking exactly like the previous one because we're just not including the median. So we have this. Yeah. And then we have this, right? So in this case, I think these are actually labeled wrong, but don't worry about that. Because, oh well. All right, wait, actually they're labeled right. They're labeled right. Never mind. They're labeled right. Yeah. So what we have now is we have we have 2 halves, right? You can think of it around the median because again, we're not using the median. So we have this half and we have this half. So what we need to do is we need to take the average of the right half and the average of the left half, or because in this case, only 2 of each. So we find the median of the right half, the median of the left half. And then we just, in this case, it's just averaging 4 and 5 and averaging 2 and 1, and then subtracting off. So we get 3, right? And then we'll look at the code in a second. We'll go back to it and we can kind of see how that's fun. And then for mod 4, we get 2, right? Again, this is a even length, so we use the median. So in this case, we're using the median, we have this half, right? And this half. And here, it's actually a lot like the first one, because in finding the median of the left half, this is just the middle one, right? And for the median of the right half, it's just the middle one. So do 5 minus 2. Yeah. But looking at how that works with the code, right? Notice that we will be a total of at most like 3 behind, like end will be at most like 3 behind where, or 3 behind this null. So like 2 behind everything else because we check if next is not null. And if it is, then we stop, right? Which is why in this case, for this last one, right, next value is the 6. And so that's why for this last case, right, that's what Q3 is. Oh, okay, well, sorry, I said that wrong. Next Q3, because we're not looking at n, we're looking at Q3. Q3 is next is 5, right? And its value is our 5. That's the medium that we have. So we have to make sure that we're not just like in this case, I remember like how I said that we know it's the lower half so we can average them. And that's true for that case, but for other cases it's different. So for example, for this one, right, we can look at the case. This is Q3, right? We have to move forward to. The reason we have to move forward to is because with the way we went about our fast and slow pointers, we moved fast, like 3 forward each loop, right? Another way we could have gone about this, if we wanted something slightly different, for example, is had a counter, right? And then 1 out of every 4 advanced the slow one, 2 out of every 4 like advanced the medium one, 3 out of every 4, right? So we can use modules for that as well. But this is also a way of going about it that I think looks a lot cleaner, but it like all of these ways. But the way this way works, right, is we're basically just looking at the 4 cases. We say, okay, what's the way we calculate them in all 4 of these cases? And then we can always simplify to these cases by just using this while loop, and then everything simplifies to just these. Hopefully that makes sense. Okay. So any questions about the quiz? If you do, message me on Slack or Joshua or your professor. Well, I guess ideally me or Joshua first. If you have a question, or you can put it in like general, doesn't matter. Okay, so cheating collaboration policy. So hopefully I don't have to tell you all this, but if I do, hopefully you hear it loud and clear. Right? Sharing, copying, borrow, code structure, looking at other students' code, or providing code. Plagiarism, dishonest behaviors are all academic dishonesty, which is a big no-no. Information cannot be shared by students except for just conceptual discussion, right? Conceptual discussion, or anything you say from the internet, make sure that you reference, reference the resource used. And then, looking at pieces of code or like sharing code, you just can't do it. Okay, don't do that. Don't share your code. Don't take other people's code. Not cool. And then it's not good for you in general, but then also you can get a 0, you can have decreased your final letter grade. And if you do it again, right, you'll just get a failing grade for the course. So don't do that. And either way, you'll be reported on a court, which is really, really bad. So, okay, so how about this? You can pause it, try and answer. Okay, so hopefully you've unpaused. That's why you hear me talking, or you've answered the question. But would this be cheating? Well, it's participatory, right? But what did we say about sharing code? Can't do it, right? Even though it's participatory, don't share code. And so it's still cheating. And you can still be punished for it because you just can't like copy other people's code. Can't do it. Okay. Blindly copying anyone's it's not okay. Yep. If you need help on anything except exams and quizzes, you can ask TAs. So Ava Becky says, okay, you can look at this one too. Pause and try and answer it. Okay, so you've unpaused again, unless you're stuck forever. So you'll never reach this, in which case, I don't know, I'm still talking to you. No, I'm just kidding. Okay. But yeah, is this cheating? Well, here, right, they just discuss at a conceptual level. So what do we do if we can discuss at a conceptual level? We cite each other, right? We cite whoever we talked to. And it's not cheating as long as it's on our participatory stepping, right? So again, on participatory stepping exercise is fine. You can't blindly copy other people's code. And yeah, it doesn't matter if it's friends, the internet, whatever. But yeah, you can't like for exams, for example, you can't do this, of course. It's not cheating in this case though, it's participatory stepping exercises, and they cite each other, and it's not copy and paste code. Okay. Never forget to copy code and produce the code on your own. If you're unsure, that's me, that's Joshua, that's the professor. Okay, now onto the fun topics, I guess. Like, you know, talking about cheating is never fun if you cheat. So if you don't cheat, I guess it can be fun. So maybe it was fun. Okay, but on to another topic anyway. Because none of you are gonna cheat. I hope. Okay, so binary search trees are interesting because they have some interesting properties. So a tree, right, a node-based tree structure is called a tree, right? But a binary search tree in particular is a node-based tree structure which has these properties. The left subtree of any binary search tree always contains nodes with smaller values than the current node's value. So in this case, right, if this is a binary search tree, that means that, notice there's a difference between binary tree and binary search tree. Binary search tree has these properties. A binary tree is just a tree that with each node has at most 2 children. But a binary search tree has these properties in particular. So there's a difference, and that's the difference. And these properties are that, yeah, anything to the left of 8 is going to be smaller than 8. So in this case, we see that that's true, right? Every single one of these nodes is smaller than 8. And then we have to look at, and then we expect the same thing of 3. Anything to the left of 3 is smaller than 3. That's true. Anything to the left of 6 is smaller than 6. Anything to the left of 10 is smaller than 10. Anything to the left of the 14 is smaller than 14. But then we also expect that anything to the right of each node is larger than it. So anything to the right of 8, right, to the right, we expect to be larger than it. So in this case, all of these are larger than 8. So we're good. And then everything to the right of 10. All of these are to the right of 10, right? And they're also larger than 10. So that's good. Anything to the right of 14, nothing to the right of 14. Okay, everything to the right of 3, we expect to be larger than 3. And they are. Everything to the right of 6, we expect to be larger than 6, right? So that's how we go through it. So the interesting thing on a binary search tree is that, yeah, the right and left subtrees only contain nodes which are larger. The right subtree has only nodes larger than it, left subtree only has nodes smaller than it. And that's then what the important thing about that, right, is that we have subtrees. So like we have the right tree is itself a subtree, and that is also binary search tree, right? So 10, the node with, if this were the top of our tree, right? If this were the root, this is then the subtree rooted at 10 is also a binary search tree. And the subtree rooted at 3 is also a binary search tree, right? Because of course they're gonna have these properties as well. So that's what binary search tree is. Okay, so now there are certain types of trees. So there's full. So a full tree, every node has 0 children or 2 children. A complete tree is all levels are completely filled except the last level, which has all the nodes it does have as far left as possible. A perfect tree has all internal nodes, have 2 children, and all leaves are at the same level. Yeah, and then perfect trees are both complete and full, but complete and full does not mean perfect. So let's take a minute to see what that means. A perfect tree is just like not only completely full, it's like something like this, right? It's completely full, and everything at the bottom level is completely full, right? So we're good, and everyone has 2 children or 0. Complete, that may not be the case, right? Like complete, we have this is complete because the entire bottom level isn't full, but everything at the bottom, everything has internal has 2 children, and then at the leaves, right? everything is as far left as possible. So like if we had like a 5 here, right? This would, instead of here, this is not a complete binary tree. Full, every node has 0 children and 2 children. So interestingly, interestingly, this full binary tree is also complete because everything is as far left as possible in the last level. So yeah, and all the levels except the bottom level are completely filled. So this is both full and complete, but it's not perfect because the perfect one has to be completely filled at the leaf level. So hopefully you kind of see it. Okay, that's just a brief overview of what they are. Now moving on. Full question one. Is this one full, complete, perfect, binary search tree, or none of the above? Okay, so you could have paused if you wanted to, you still can. But okay, the answer is, let's see, right? So is it full? Well, going back to our definition of full, right? Full tree, every node has 0 or 2 children. Does that apply here? Well, this one has 2 or 0. This one has 0 or 2, 0 or 2, 0 or 2, 0 or 2. Yes, right? It's full. Is it complete? Well, remember, complete, all the levels are filled except for possibly the last level. And then everything is as far left as possible. That's not true here, right? This one is not, it's higher up than these, right? So it's not complete. Is it perfect? Well, a perfect tree at least has to be full and complete. That doesn't mean you'll have a perfect tree, but it better be both complete and it's not. Is it a binary search tree? Is everything to the left of 25 smaller than it? Is everything to the left of 11 smaller than it? 4? Now to the right of 4, larger, to the left of, or right of 11 larger, right of 25 larger? Yes. So it's both full and a binary search tree. And then here's the explanation for it as we went over. Right. Okay, and we'll just assume for this class, all sorted trees are gonna have unique values. Okay, so is this one complete, full, perfect binary search tree? Okay, let's see. First thing, is it full? And you can pause if you want to, but is it full? Well, does everything have 0 or 2 children? No, right? This one only has 1 child, so it's not full. Is it complete? Yes, because the only level that we don't have completely filled is bottom layer, and it's all the way to the left, right? So it's complete. Is it perfect? No, right? This bottom level is not completely full. So it's, so far we only have complete, or so far we only have, yeah, complete. So far only complete. Is it a binary search tree? Well, it might look like it at first, but it's not, because to the right of 14 is 51, but also to the right of 14 is 25. Oh wait, that's okay. Sorry. And everything to the left of 14 is smaller than it. Everything to the right of 5 is, you know what? I think I misspoke. This is a binary search tree. Yes. It is a complete and a binary search tree. So yeah, the reason why it might look like it at first is because it is. Ha, it's tricking you all along. Okay. Yeah. And a complete binary tree is full up until level n minus 12. Right. And it may not have to be at the last one. Okay. This one. You can pause if you want. And now you've probably unpaused. So yeah. This one is it full? Well, everything has 0 children or 2 children, so it's full. Is it complete? Well, everything is as far left as possible, except possibly the, everything is as far left as possible on the leaf layer, and everything is full except for the leaves, which is true. But is it perfect? No, it's not perfect because we don't have all of our leaves filled. It would be perfect only if we had 2 children from 51, which we don't. Not perfect. Is it a binary search tree? No, it's not a binary search tree because left of 2 is 5, and 5 is larger than 2, so it's not. So we should only have full and complete. Okay, so how about this one? So hopefully it should be kind of clear that this is based on these examples, right? This is perfect, right? And it's perfect because at the we have every layer filled completely. So it's perfect. And if it's perfect, we know it's complete and full. The other way around, we don't know. Well, if it's perfect, we know it's both full and complete. So binary search tree, is it? Well, let's see, right? Again, this might look like it at first, right? It looks good, but then we notice something kind of interesting, which is that to the right of 14, somewhere in here, right, we have a 5, and 5 is not larger than 14. So automatically knows this is a binary search tree. Same thing over here. To the left of 14, it's something larger than it. So it can't be a binary search tree. So it's only the first two. Yeah, perfect binary trees have 2 to the h minus 1 nodes. 2 to the h because, or 2h minus 1 because the height of the tree is h, right? The height. And then each of them we have increasing powers of 2, right? Of them. So we have 2, 4, and then 8. And if you remember, the summation actually is kind of interesting, I think. Summation, whoops. Summation of 2 to the 8, or let's go, yeah, 2 to the h. That looks really good. That's good handwriting. For like, we're going, yeah, through the heights, right? And let's say it's like from 1 to n is equal to like 2 to the n minus 1, right? Or sorry, 2, sorry. If we sum them all up, yeah, that's 2 to the n plus 1, sorry, minus 1. You may remember that identity. And in this case, right, our height happens to be 3. So we're going to have 2 plus 1, right? Then we're going to have 2 to the 3 minus 1 is 7. Let's see if it is right. Yeah, 1, 2, 3, 4, 5, 6, 7. And yeah, this h, I guess I should have written n or I or whatever, but okay, let's just call it. H runs from like 1 to 10. And yeah, in this case, right, it's 0, 1, 2. So we can actually also just write it to me. Okay. So that's what we can talk about. All right, types of trace traversals. So there are a few of them that we're going to talk about. There, if we think about it, for each node, we can either go to the node first, go left first, or go to the node first, go left first, or go right, right? So node left, right, left node right, and left right. Okay, well, yeah. Basically, sorry, we can go to the node first, we can go to the node second, go to the node last. We're always gonna do left before right. Okay. So yeah. So we can either, if we do left first, then we're gonna go like this, right? Yeah. Sorry. Yeah, that's right. Or yeah, if we do node first, we're gonna do A, we're gonna do B, D, H, and then the next thing we do is we're gonna do A, B, D, H, I, and then we already did B, so we're gonna go to E, we're gonna go around, we're gonna C, F, G, J, right? For in order, right? We go to the node first. We go to the node, and then we go. Oh, sorry, that was pre-order. Pre-order go node first. Sorry. In order, we go node second. So we go as far left as possible. So go left, 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 left. Then we start at H, and then after that, right? Well, we can't go left anymore. So then we actually have to like go back up the tree. So go D, and then we go I, right? Because now we have to go right. And then we go after I, or after I, we go to B, right? Because we're going back up. And then we go to E for in order. And then go back into A. And then we do the same thing on the right half. And then for post order, we're going to go left, then right. The nodes, we're expecting that A will be the last thing. So we'll go left, as far as possible. So first we get H, then same as before, I, D. Well, yeah, H, I, D, because again, we do the node last. Which is why we do D now. And then we do E, E. And then we go right, right? So, or we go right and then left, so then F, and then after F, we have go over. We don't go until the node until we've hit all the leaves. So J and then G and then C and then A. So maybe that was a little confusing, but hopefully you can kind of see with the picture. Okay. Now for the level, there are a couple different traversals. One is called level order. So for level order traversal, we have something called breadth first search. So the idea behind a breadth first search is you go one node away from your root. And this works on graphs as well as trees. So maybe you've seen this in like discrete structures, but a breadth first search, you start at your root and then you go distance 1 away. So you do all the things distance 1 away. Then you do all the things distance 2 away. So start at the root, you go distance 1 away. So both of these at like the same time. And then you do all the things distance 2 away. And all the things distance 3 away. So for a tree, that looks pretty nice because we can just see it in levels. So you go like this. Right? And that's the way of seeing it. You can go spiral, or you can think of it like a zigzag. And so, yeah, that's what we have. And then two different approaches, right? We get you something different, like if you go 5, 10, 15, or in this case, it's 10, 4, 8. Actually, they should be in the same kind of order, but in this one, like we switch every level, right? Oh, and this we do too. I mean, I guess it's, but you can think of it in two. Okay. Okay, so I know it was a lot. Hopefully, you haven't followed, but let's see. Pre-order of this traversal. Okay, so now going over it, remember for pre-order, we're going to go, remember, so here's how I think of it, right? There are three different ones. Pre means like you do this before. So pre, the very first thing you do is node. And then left always comes before right. So node, left, right. And then in order, well, like, okay, it's in order. So like the node goes in the middle, right? So L, N, R. That's how I always remember anyway. And then post order, post means last. So again, L always comes before R and N comes last because it's post. Okay, this one's pre-order. So N comes first. So, okay, so node, left, right. So we do node, and then we do left. And remember, basically what this means is that as we're going through it, what node, left, right means in this case, right, is that as we're going through it, we pick up the nodes when we see them. But then the direction we go is left first. We prioritize going left over going right. But as we see nodes, we pick them up. So we pick up the 5, we prioritize going left. We grab the 3. We prioritize going left, we grab the 1. Okay, we can't go left anymore. But we prioritize the node we're already at. So we go right. So we pick up the node when we see it. Now we can't go any further, so we go back up to where we were. We prioritize going left or right, we already went left, so we go right. We can't go any further, we go back up. Prioritize left or right, we already went right. So we get 6 now. So far we've had 5, 3, 1, 2, 4, and 6, right? Again, can't go left, so go right. Now we prioritize left over right, so choose 7, and then we choose 9. And the answer, I believe, is this one. Let's see. Yeah. All right. So in order, traversal of this tree is, so again, in order means, okay, well, we have pre, post, and in. So in order, like the N is in between, right? So let's count with that. Huh, that was great. Good job, Andrew. Thanks, Andrew. Okay. Huh. But we go left node, right. So now we don't pick up the node until right before we go right. So we prioritize my left first. We don't pick up the nodes until we go, until after. So before we go right, or try to go right. So the first thing we do is we actually go left. We go left again. And now, Well, now we can't go left anymore, right? So for in order, we go left, left, and now we can't go right anymore. So we're gonna pick up the one, or we pick up the one before we go right, right? And then we're still at the one, so we go right, right? And then we try and go left, we can't. So we just pick up the node, then we try and go right, we can't. So far we have 1, 2. So I mean, okay, this is gonna be our answer, right? But we're not done. Let's just go ahead and finish it up. So then we go up the tree, then we go back up, right? Because we've finished everything here. And now, but before we go right, we pick up the 3. And then we already went left, we pick up the node, so now we go right. And so we're gonna pick it up because we try and go left, we can't pick up the node. Then we try and go right, we can't. So the next thing we do, and it's called in order because also, if you'll notice, if it's a binary search tree, you're always gonna get a list that's in order. So good thing to know. But okay, the next thing is the 5, right? These are at left. Now we're gonna pick it up, then we're gonna go right. We pick up this one because we can't go left, so pick it up, then we go right. Yeah, we go there, we pick it up, then we go here. And the first thing we do is we can go left. So we pick up the thing on the left, we go left, we pick it up because we can't go left or right, or we can't go left, pick it up, can't go right. So we go back up. Now we already went left, so we pick it up. Then we go right, we pick that up. So it's in order, and this is our answer. Yeah, so there you go. Okay, so now post order, of course, right? So post, last, right? So go left, right? So what this means is we only pick up the node after we visited both the left and the right. So we go left, we prioritize going left always. Prioritize left, prioritize left. Now we can't go left, so we go right. So go right, and then we can't go left or right, so we pick up the node. We go back up. We already tried going left, we went right, pick up the node. Now we go up. Well, we've gone left, we haven't gone right, and right comes before we have to go right before we pick up the node. So go right, can't go left or right, pick it up, right? Because we do go left and right, just nothing there. Then we go back up, and well, we've gone left and right, so we can pick it up. So far we have, I think it's 2, 1, then 4 and 3. Yeah, 5. Well, we haven't gone right yet, so we can't pick it up yet. So we have to go to 6 and 6. We can't go to 6 yet, right? Because, or we go to 6, right? We can't go left, so we have to go right. We go to right before we pick up nodes. And then here, we can go left, so go left, right? And then when we're at 7, we try and go left and right, and we can't, then we pick it up. So 7 comes after this, after these, and then we go back up to 8, but we can still go right. So go right, we can pick up the 9. And then we go back up, right? We've gone left and right, so then we pick up the 8. We've gone left and right on the 6, pick up the 6. Then we go left and right on, we've already gone left and right on the 5, so pick up the 5, and we're done. This is our answer. Let's see, right? Yeah. Post order, we visit the root node after we visit both subtrees. Okay, so depth and breadth first search. So we just talked about, like pre, post, and in order traversals, and these all walk through nodes, yeah, with a depth first search. And depth first search means you go as far as you can in a direction before you can anywhere. Depth first search means go as far as you can in a direction until you can't anymore, and then return back to where you were. So it's kind of like, I like think of it like a maze. Like you're going through a maze. When you go through a maze, right, you keep going until you hit a wall and you can't go any further. So then you go back to the last decision you made. And that's exactly how depth first search works. Like you go until you can't anymore, and you're like, oh well, I can't go anymore. So go back to the last place in which you made a decision, right? You went left or right, and now there, just choose the other way, for example. That's how depth first search works, both in graphs and in trees. So you select the next node and you keep going as far as you can before you're going back. So you completely explore a subtree before taking another route. And pre, post, and in order are all depth first searches. Only pre-order accesses nodes with a DFS in the same one. Yeah. So yeah. And accessing means like picking up the nodes. That's what I was calling it. breadth first search, you actually is the level order traversal we were talking about a minute ago. At a breadth first search, you completely explore one level before you go to the next. So in this case, for example, that would mean we go to 5, then 3 and 6, then 1, 4, 8, then 2, 7, 9. So that's breadth first search or level order traversal. It means the same thing, just level order is what we call it for a tree. So you explore the root and explore all the neighbors before going on, right? Okay, so this is a poll question. So given this binary tree, what are some permutations of the orders in which the nodes are accessed using a depth first search? Yeah, access means the node's property or use. So basically we're looking for value of node, right? Okay. Right, so for when we're looking at depth first search, right, there's no inherent left or right. So that's a hint, yeah. Okay. So the first thing, right, is generally, remember, accessing, like if you want a depth first search, you have to think of it as like pre-order. Right? But it doesn't necessarily have to be exactly like pre-order. It's just the way access it. So for example, we have to access the 5 first, right? And then we go as far as we can in one direction. Oh, one direction. That was a band. Pop culture. Okay, so 5 and 3 is one way to go about it, right? And then we go 1. And we're going as far as we can in one direction before switching. So as far as we could in this direction. So then we go this direction. And we can't go any further, so we backtrack. We backtrack again because we can't go anywhere. So now we go down. Wait, pick up this. So we go back up, way back, and then we go here. We go here. We go here because remember, so far we've noticed we're actually prioritizing left over going right, just the way we've been going about it. And then we can't go any further, so we backtrack. Then we come back down and go here, which is actually this one. But remember, we didn't necessarily have to go left first for depth first. We could just go say, oh, we're going right first. So we 5, 6, 8, 9. We can't go right or left, so we backtrack. And then, oh, we can go left. Okay. So we go up, we have to backtrack, backtrack, backtrack. Okay, now we can go left. Pick up the 3. We've been prioritizing right, so do that. Have to backtrack, left, and right. Now what we notice is this is actually exactly this answer. So really the only 2 ways of going about it are those, so B and D. Okay. Yeah. And that's really weird, but okay. Okay. So yeah, we can kind of see it, exactly what we were talking about, right? Yeah. Actually, this is even better visual. We have to backtrack, and then we go right. And then we have to backtrack, right, left, backtrack, and then we visited everything. And we do that by backtracking all the way back to the root. We've gone left and right. So the other way of going about it, very similar. Right. Then we have to backtrack, left, backtrack, left, right, backtrack, left, and left, or left, and then backtrack, and we're done. So okay, so for this one, our valid permutations are the orders in which we access them in a breadth first search. And remember, again, we're just going to access the values. So yeah, remember breadth first search is like you go further and further away with each iteration. Yes. Can I pause? Okay. So yeah, again, for breadth first search, we go level by level. So we go 5, and then we have a couple options, right? We can go 3 and 6, and then go 1, 4, 8. And then we go 2, 7, 9. Right, we just go level by level, like level 0, level 1, grab all the ones at level 2, and then grab all the ones at level 3. And we go, in this case, we're going to go like basically left to right. And that's one way of going about it. And if we go left to right, then that's 5, 3, 6, 1, 4, 8, 2, 7, 9. We could have also gone right to left. So go 5, 6, 3, 8, 4, 1, So yeah, 563, 841, 972. I was just making sure the answer is there. It is. Okay, cool. So yeah, but those are the two ways of going about it, right? We go basically prioritize going right first, prioritize going left first. Those are the two ways of doing it, or two ways of seeing it. So we're going to expect A and C. And the way we actually write the code for this, we'd have to use a queue. And we go level by level. We never search the node of a greater depth while there's a node. That's a really important invariant, or really important thing that always remains true as you go through, is that you're guaranteed that anything you, with depth first search in general, you're guaranteed that, especially with trees, like you don't have to do any extra work, but you never search the node of a greater depth before you finish all ones with this step. So that means we go over to 3 and 6 before we ever hit 1, 4, or 8. So that's always like, that's really useful actually. But in some algorithms things, but okay. But yeah, the way you go about it is a queue, right? Because we say, okay, 5 is in our queue. Okay, we add its children to the queue. So now we have 3 and 6 in our queue. Okay, well, we're done with the 5, so we can remove it from our queue. So we see the 3. We add the 1 and 4, its children, to our queue. And we're still on level 1. We can remove the 3 because we don't have any more use for it. And then our 6 in the queue. Okay, so now we can remove the 6 and put its children, which is just an 8. And we keep going down the tree. But if you notice, we're actually done with the first 2 levels. And we always hit those before we ever touch anything in any of the following levels. Yeah, that's how that works. So, okay. And right, and these are the two ways to go about it. Right? We go prioritize left, we prioritize right. Those are the two ways. Or breadth first search. Yes. Remember, breadth. I guess like one way of going about it is like breadth. Like it's like kind of like being well-rounded. So like you're good at doing everything. So you like do everything a little bit at a time. I don't know. I usually think of it as like depth first search. You're going like as deep as possible through like a tree. And breadth first search is just like the other one. Okay. So yeah, which of these are valid array-based binary search trees? So X an empty null value, the next one is where there is. So you can pause. Okay, so let's think about it. So the next one is our root. So let's try the first one. So that'll be 5. Its children are 3 and 6. And then 3's children would be 1 and 4. And 6's children are nothing, and then 8. Right. So that's how we build. The next one we build, it's 5, 4, 3, and then 2, 1, nothing, and then 0. I'm just going to put a line between them. And the next one, and hopefully you kind of see how I'm building this. 9, and then 5 is our left child. And then it has no right child. The left child of 5 is 2. Right child of 5 is 6. Right, then we're done, right? So then we have 7, 4, no right child, 3 and 5. And then, 7, 4, nothing. And then 4's children are 3 and 5. And yeah, we have like nothing and 9. So I think that's how this is. Pretty sure. I might have messed up somewhere, but okay. I think this is right. But okay, let's look at it. Well, when we do this, right, we have 5. Is this first one a binary search tree? Everything to the right of 5 is larger. Everything to the right of 6 is larger. And then also like nothing smaller is on the left in this right subtree. And then here, everything on the left is smaller. To the right of 3 is larger. To the left is 3 smaller. So A is good. So B, left, everything smaller. What we notice here is a problem. To the right of 4 is 1. So that's not good. How about this one? Everything to the left is 9 is less, which is good. Everything to the right of 5 is greater, which is good. And everything to the left of 5 is less. So this one's also good. And for this one, well, we have a 9 in the left half of 7. So already we know it's not good, right? Because left half of 7 is 9. So only A and C. Yeah, so array-based representations of binary trees can be inefficient. We'll see later in the course, I guess heaps are a really good use case for them, but a lot of empty space maybe they're not so good. Oh yeah, so I guess I didn't really explain this, but maybe I should have. For actually building the tree from the array, the parent is the I divided by 2, 1. And then, yeah, if it's 1 index, if it's 0 index, it's I minus 1 over 2. So these are just like ways of seeing it, right? So in this case, it's 1 index. So its children are going to be 2i and 2i plus 1. So 5 children are 3 and 6. 3's children would be 4 and 5. Or no, sorry. Yeah, well, because it's 2, right? Index 2. So that's how I was building it, right? And yeah, and maybe you kind of saw that, but this is like the actual equations for what you'd use for them. So as we saw, A and C. So this is A, right? This is B, C, and D, just as we saw. Yeah. And yeah, yeah, this 9 will actually be out of the treaty altogether. So I guess it's, I did mess up a little bit. Like I said, I probably did. You know, I'm human. It happens. This 9 is out of the tree altogether because we notice, I mean, the only thing, like, there's nothing in the 3. Like we do 3 times 2 plus 1, it'd be 7. So we'd expect that to be one of the children, but there's nothing here. So it's a child of, well, nothing. So, so even though a 9 isn't in the left half here, it's still not valid. A valid binary search tree. You can't have things floating around. Okay. Anyway, given a binary tree root node, determine if it is a binary search tree. Okay. Let's see. Left. We're almost done. Sorry, I know it's kind of long. So hopefully we'll be done. Okay. Assumptions you can make for a binary search tree is that the left subtree of a node contains only nodes less than it, and the right subtree contains only nodes greater than it, right? But both of them have to be valid binary search trees. So we return true or false. So maybe you see this, and you can work on this problem. Maybe you see this and you see, okay, there's some sort of like structure here that's true for the root, and then both the root's children. So maybe that leads you to a certain kind of solution. All right, so maybe it leads you to something like recursion, right? Because it has to be true for the left, has to be true for the right, and it has to be true for the parent. Yeah, so you can start off by thinking what makes it valid. So the left subtree of the node contains only smaller nodes. The right subtree of the node contains only greater nodes. So each subtree itself should be a binary subtree. So that's what indicates the recursive structure. Think about how to recurse the tree and then write the code. So, okay. So you can work on that. And the code is on the next slide. Okay, so yeah. In this simple but wrong solution, we check that every left node is less than the parent, and check that every right node is greater than the parent node. But the thing is that this, yeah, I just wanted to make sure I was recording, so that was interesting. Okay, but yeah. And we check that every node is greater than the parent, which seems good, right? But there's a slight problem with that, which is that we don't remember everything about the subtrees, right? So like if we have like 5, 4, 6, and then here, we want something smaller. So if we take like a 3, well, 3 can't be on the right half of the 5. So it looks right, but maybe it's not because of that, right? We don't actually check the subtrees and that they're valid, the original one. So why is it wrong? So here we see an example. It returns true in this situation, it should return false. So we see the problem. 4 is greater than 3, it's in the left half. Oh no. Okay, so now a correct solution. How do we fix it? Well, we can instead, for example, get the maximum, like store the maximum of the subtree. In this case, we would know, well, for the 2, we store what was the maximum of the left subtree, and that's 4, because that's larger than 3. It's not valid. So it's very similar to the previous one, except we're also using the max. So it keeps track for the left half. And for the right half, we have to have a min, right? So like in my example, right, the problem was we needed a min. So yeah, on the right. So on the right half, we have to have the minimum of the whole right half and the maximum of the whole left half. So we reduce the max value allowed for the node traversing. It only returns true if the binary search tree is valid, and it returns true for all the recursions. I noticed that because we have an and here. So this has to be true, and this has to be true. So it has to be that both the left is valid and the right is valid. And then like the right is larger than this one. The max from the right is larger than this one. And the min from the right is larger than this one. And the max from the left is smaller than this one. So that's how we're searching. Questions about that? And it's a little confusing. Yeah, that's a good question. So some exercises at home. So validate binary search tree is kind of similar to what we're doing. You can see all these kind of, practice a little with binary search trees. Also step epic questions. Step epic is epic. Okay, but yeah, you have an honor luck quiz due Wednesday. So make sure you do it. So more in-depth DFS. So let's do this one. Given this, which of them are valid? Well, valid depth first searches again. We start at the root, right? And again, we're going to favor one. We can have either favor going left or favor going right. Which one takes precedence? Let's do left first. So we do 5, we do 3, then we go 1, and then we go 2, right? And then we go back up, right? And okay, here we can't go left, right? We can't go right. We already went there. So then we have to go right. And then we backtrack, and go right. Go right because we can't go left. Favor going left. Backtrack, favor going right. Or no, backtrack, then go right because we already went left, right? So, okay. But now the other way to do it, as we've discussed before, going right, like has higher precedence, so go right, and we access them as we go. 5, 6, 8, 9, right, then backtrack, left, backtrack, left, and then we go left, grab it, go right. We can't go any further, we backtrack, go left, and we go right because that's what we prefer to do. We backtrack, and we go back to the root, and we're done. So those are the 2 ways of going about it, right? And I guess this is also an important thing to mention is that a really good way to do DFS is with recursion. And the reason why recursion is so good for DFS is because in essence, DFS uses a stack. But remember that the call stack is itself a stack. So that's why we can use recursion for this, which is actually really helpful. But also, yeah, you can also just use the stack data structure as well. But the idea is basically what you're doing, right? Is you're putting the 5 onto the stack, right? So we have like 5 on the stack, for example. Let's just do the left first example. Put 5 on the stack, go left. And then we put the 3 on the stack, right? And we're also printing them as we go, I guess. So we print the 5, we print the 3. Then we go left, we put a 1 on the stack. And I'm putting them before because with a stack, right, you put it on top. So then we can't go left, right? So we have to go right. So go right, put a 2 on the stack. Well, 2, we try and go left, we try and go right. We can't. So we actually pop 2 off the stack. Then we go back up. And we have a 1. We can't go left, we already went right. So we can pop 1 off the stack. So this is how bad the backtracking works. We go back up. We already went left, so we can go right now. So now I put the 4 on the stack. We print out the 4 maybe. Then we try and do something with the 4. We can't, right? No left, no right. So we remove it from the stack, we pop. Then we backtrack. And now we have the 5, we go right. So put the 6 on the stack. Can't go left, we can go right. So now we can put the 8 on the stack. 8 on the stack. Then we put 7 on the stack. Then we can't go left or right, we pop the 7. We backtrack, we put the 9. Can't go left or right, we pop the 9. We go back, we backtrack at 8, we backtrack at 6, and then we backtrack at 5, and we're done. So notice how that gives us the exact same thing. So that's because the way we would do this is a stack. So depth first search, stack, breadth first search, keep. So yeah, that's how it works. So we can actually see exactly this. Our stack 3, 7, 9, and oh yeah. Well, okay, we can also think of it this way, right? Is we can just put them on the, another way of doing this, right? It would just be to put them on the stack right away, put both children on the stack. So both will essentially work. If we mark, like if we mark the right child is not visited and left child is visited, like the way I was just describing, also works for stack. But the way we're doing it here, I guess I should have put this first, so I would be consistent, is we're just adding them both to the stack. And then whatever we access, we just pop from the stack. And this way, I guess, it's a little more efficient. And so it's another way that also works. So we go 5, we pop, and then we put the 3 and the 6 on the stack. And then 3, we add both the children. So we add 1 first, and then 4. We have 1, 4, 6, and we pop the 3. And we have 5 and 6 we have been accessed. Oh, sorry, we're going right first. Sorry, the way I was just driving it, we go left first, but okay. The way in which we go right first, we access 5, we put 3 and 6, and 6 is on the top of the stack. So they had top of the stack on this side, but okay. Then we delete 6, we add its children 8. We delete the 8 after we access it. We put its children 7, 9. We have 7. Oh, actually, we're going right first, so actually it'll be 9 first. 9, then 7. And then we finally get to the 3. And this 3 is here. And so we go 3. And we put its children 4 and then 1. And we go 4, access. We have 1. And we're going to access it and put 2 on the stack. We're going to pop the 2 afterwards. And we can't go any further. So this is what we'll get. And that's why we get this answer. So hopefully you can kind of see how this goes about it. So we'll go through it. 3, 7, 9. We can pop them, right? Access 9, access 7, pop them in the stack. Then we pop 3 and put its children on. We go 4. Then 1, we pop the 1, put its children on this one child, access it, and we're done. So again, the whole idea is you just go as far as you can, so you can't go any further. And that's it. So sorry it was so long, but hopefully learn something. And if not, hopefully shows that. That's it. Thanks for coming to the discussion today. And see you next week. If you have any questions, just email me or message me on Slack.